This is a tugboat and it can pull a ship 400 times its own weight. The ship it's moving has engines powerful enough to cross the Pacific Ocean. It has a rudder the height of a 4-story building and enough horsepower to outrun most naval vessels. And yet it cannot move through a narrow canal, enter a port, pass through a tight strait, or reverse into dry dock without this tiny boat pulling it into position. Here's why. At sea, a large container ship is one of the most capable machines ever built. It maintains course across thousands of miles of open ocean, adjusts for weather, and responds predictably to its controls. The crew is in command, the engines are efficient, and the rudder does exactly what it's told. Then the ship reaches the entrance to a port, the mouth of a canal, or a narrow strait between islands, and almost everything that makes it capable at sea stops working. The problem is the rudder. A ship's rudder generates steering force by deflecting water that flows past it as the vessel moves. The faster the ship goes, the more water flows across the rudder, and the more control the crew has over direction. At 20 knots in open water, the rudder is highly responsive. But entering a port or navigating a canal, the ship slows to 1 or 2 knots, sometimes less, and the water flowing past the rudder slows with it. At that speed, there is barely enough flow to generate meaningful steering authority. The rudder becomes, for all practical purposes, decorative. The captain now has 200,000 tons of steel moving through a confined space, with almost no ability to change direction, and the walls are getting closer with every passing minute. Then there is the stopping problem, which is considerably worse. Large ships have no brakes. The only way to reduce speed is to run the main propeller in reverse, and for a fully loaded vessel at sea, stopping from cruising speed takes around 5 miles. 5 miles of open water just to cancel forward momentum. That distance simply does not exist inside a busy port or a narrow canal. And even if it did, running a propeller that size in full reverse inside a confined space creates a wash of churning water, powerful enough to batter surrounding vessels, damage port infrastructure, and tear sediment from the seabed in quantities that can block the ship's own cooling intakes. The engine that moved the ship across the ocean is precisely the wrong tool for the final few hundred meters of its journey. This is the reality every time a large ship needs to move slowly through a constrained space, and it happens dozens of times a day in ports around the world, in canals connecting oceans, in straits threading between islands, and in dry docks where ships go for repair and maintenance. Every single time, the answer is the same. You call a tugboat. Most people think of tugboats as a port thing, small orange boats, shuffling container ships sideways into berths. That's part of it, but it's a narrow view of what these vessels actually do and where they operate. In Indonesia, a country of more than 17,000 islands, with one of the largest shipping industries in the world, tugboats are essential to moving large vessels through the narrow straits and channels that separate the archipelago. There is no wide open approach, no room to slow down gradually over several miles. The passages are tight, the currents are unpredictable, and a vessel that loses directional control in those conditions does not drift harmlessly into open water. It hits something. Tugs work those straits constantly, not docking ships but escorting them, holding them on course, and counteracting the lateral push of current against a hull that cannot steer itself at low speed. In Alaska, after the Exxon Valdez disaster in 1989, the state mandated that all oil tankers navigating Prince William Sound be escorted by purpose-built escort tugs. The Sound is full of rocky outcroppings and reefs, and a tanker carrying millions of barrels of crude oil cannot be allowed to navigate those waters alone at any speed. The escort tugs there produce around 13,000 horsepower and are built to respond within seconds if a tanker loses steering or propulsion. Their job is not to move the tanker. Their job is to catch it if it starts going wrong and to hold it off the rocks long enough to regain control. Aircraft carriers present a different version of the same problem. A Nimitz-class carrier is 1,100 feet long and displaces around 100,000 metric tons. At speed, it maneuvers reasonably well. But when entering a port, reversing into a dry dock for repairs, or navigating a tight harbour approach, it has exactly the same slow speed control problem as any other large vessel. The consequences of getting it wrong are considerably expensive. Carriers typically require several tugs working in coordination when entering or leaving port. Some push, some pull, and others hold the stern in position while the bow is guided into alignment. The common thread across all of these situations is the same. The vessel is large, the space is confined, slow speed has eliminated meaningful steering control, and external force applied precisely from outside the hull is the only practical solution. The tugboat is that solution. The maritime industry uses a metric called bollard pull to measure a tug's capability, and it is a deliberately simple idea. You attach a tug to a fixed point on shore with a heavy line, instrument the line with load cells, run the engines to full power in calm water with no current and no wind, and measure the sustained force the vessel can apply. That number in metric tons is the bollard pull rating. Not horsepower, not torque. Force applied at zero speed, because zero speed is exactly the condition under which a tug does its most important work. This distinction matters more than it initially seems. The Ever Given, the container ship that blocked the Suez Canal in 2021, has a main engine producing around 80,000 horsepower. A typical harbour tug produces between 4,000 and 6,000 horsepower. On horsepower alone, the comparison is almost absurd. But horsepower measures how quickly work is done across a distance, and it is optimised for sustained movement at speed. Bollard pull measures something different: how much force a vessel can exert while stationary. In a port or a canal, where the entire operation happens at speeds measured in fractions of a knot, bollard pull is the only figure that tells you anything useful about what a vessel can actually do. A standard harbour tug generates between 40 and 80 tons of bollard pull. That figure sounds modest until you consider what it is being applied to. Bollard pull is a small number compared with a ship until you think about the context. The ship is already floating, so gravity is not a factor. It is already largely free of friction. It is, in a sense, already wanting to move. The tug is not fighting the ship's weight. It is fighting inertia and the resistance of water against a hull that is starting to shift. And in calm water, those forces are far smaller than the raw tonnage implies. Once the hull begins to move, sustaining that movement takes considerably less force than initiating it. The world record for bollard pull belongs to the Island Victory, a Norwegian vessel that produces 477 metric tons of continuous pulling force from 42,880 horsepower across two Rolls-Royce Bergen engines. The Island Victory is not a harbour tug. It is an offshore anchor handling vessel built to install oil rig moorings in the North Sea, a job that involves dragging enormous steel anchors into the seabed against massive resistance. The harbour tugs working the ports of Rotterdam, Singapore or Los Angeles operate at a fraction of that power. The point is not the record. The point is what even a fraction of that capability can do when it is applied to a floating object in calm water with almost no friction to fight. Everything about a commercial ship is designed around one goal: moving the maximum cargo across the maximum distance for the minimum fuel cost. Engines are sized precisely for that task, no more. Hull shapes are optimised for forward movement at speed. A tugboat is the deliberate opposite of every single one of those priorities. Where a cargo ship is lean, a tug is overbuilt. Where a cargo ship is optimized for speed, a tug is optimized for force at 0 knots. The result looks like a floating engine room with just enough hull around it to keep the water out, because that is more or less what it is. The most visible expression of this is the propulsion system. A conventional ship uses a fixed propeller at the stern and a separate rudder to steer, and that arrangement has one fundamental problem. The rudder only works when water is already flowing past it. At slow speed in a confined space, it is nearly useless. Modern tugs replace the entire system with a Z-drive azimuth thruster, a propeller mounted in a pod that rotates a full 360 degrees. To go forward, you point it backward. To push sideways, you point it sideways. To reverse thrust instantly, you rotate 180 degrees without touching the engine. There is no rudder because the propeller has absorbed its function entirely. The Z-drive name comes from the drive shaft geometry. Power enters horizontally from the engine, bends downward through bevel gears, then bends again to drive the propeller horizontally. 2 right-angle turns in the power path trace the letter Z. Around the propeller on most tugs sits a caught nozzle, a steel ring shaped like an aircraft wing in cross-section that completely encircles the blades. Water entering the nozzle accelerates through the narrowing channel before reaching the propeller, generating more thrust per revolution than an open propeller could produce. Caught nozzle technology increases efficiency. The nozzle also generates thrust of its own because the pressure difference between the faster water inside and the slower water outside creates a forward pulling force on the ring, transmitted directly to the hull. The propeller moves the water. The nozzle harvests the pressure difference that movement creates. None of that matters if the tug cannot hold its position while applying it. Most fast small boats use a planing hull, a flat-bottom design that rises onto the water surface at speed. Put that hull on a tug, apply full power against a 200,000-ton ship, and the tug skips sideways. No grip. A displacement hull is the opposite, deep and curved, shaped to sit in the water rather than on it. When a displacement hull tug pulls hard, the reaction force pushes the hull deeper, which increases resistance and locks the tug more firmly in place. The harder it pulls, the more securely it grips. A truck needs the road for traction. A tug needs the water, and the displacement hull is how it gets it. Here is where most explanations lose people, because the numbers feel impossible. A 200,000-ton ship is a mass that breaks ordinary intuition. The idea that anything connected to it by a rope can move it seems like it should violate something fundamental about how forces work. But the critical distinction is between moving something and lifting something, and in engineering they are completely different problems. To lift 200,000 tons, you would need to apply an upward force equal to gravity, acting on all of that mass at once. Gravity is doing the heavy lifting there. To move 200,000 tons horizontally in water, you need to overcome its inertia, and then the resistance the water creates against the hull as it begins to shift sideways. These are radically different numbers. The ship is floating, which means the ocean is already carrying its entire weight. The tug is not fighting gravity at all. It is fighting the reluctance of a large floating object to change its state of rest, and the hydraulic drag of water against a hull that is starting to move through it. And in calm water, both of those forces are far smaller than the raw tonnage would suggest. Once inertia is overcome and the hull begins to move, sustaining that movement takes far less force than initiating it. What the tug provides is not brute power, but precisely controlled force, applied at the right point on the hull, in the right direction, at the right moment. A ship's main engine is optimized to push hundreds of thousands of tons across thousands of miles. The tug is built to push a few meters sideways without hitting anything. These are not variations of the same problem. They are fundamentally different challenges, which is why they require fundamentally different machines. When a large vessel approaches a port, a canal entrance, or a confined waterway, the tugboat captain already has information about the ship before it arrives. Its size, its cargo, its draft, and the current weather and sea conditions. In most major ports, a harbour pilot, a specialist licensed specifically for that port's tidal patterns, currents, and physical layout, will board the incoming vessel offshore and direct the approach from the bridge. The tugs attach to the ship using heavy lines, typically at the bow and stern, and from that point, they are not being towed. They are actively working, pushing, pulling, holding sections of hull against the wind, correcting for tidal drift, and applying counterforce wherever the ship's mass is trying to go somewhere it should not. The whole formation, a 200,000-ton ship and several hundred-ton tugs, is being moved through a confined space with margins that can be as tight as 10 or 15 meters on either side. Each tug captain makes continuous adjustments based on how the ship is responding, what the water is doing, and what the pilot is asking for. There is a specific hazard in this work called girting, which is not well known outside the industry, but has killed people. Girting happens when a tug's tow line swings sideways past the tug's centre line, usually because the ship is moving faster than the tug or has changed angle unexpectedly. When the line reaches a certain angle, it stops pulling the tug forward and starts pulling it sideways, generating a rolling force the hull cannot resist. If the captain cannot react in time, the deck edge submerges and the vessel capsizes. Modern tugs use a restraint called a gog wire, a chain that limits how far the tow line can swing, and every tow hook has a quick release mechanism the captain can trigger from the wheelhouse in under a second. The amount of engineering dedicated to this single failure mode reflects how seriously the industry takes it. From the dock, the whole operation looks almost boring. A ship moves sideways at a barely perceptible speed. Small boats hold position around it. Nothing dramatic appears to be happening. What is actually happening is the continuous management of an enormous, barely controllable mass through a space that offers almost no margin for error by people who have spent careers understanding the specific behaviour of a specific stretch of water. The tugboat's achievement is not that it is stronger than a 200,000-ton ship. It is that it solves a problem the ship cannot solve at all. At sea, the big vessel is in its element, capable, efficient, and in command. The moment it needs to move slowly through a confined space, the physics that make it powerful at sea becomes a liability, and a machine a fraction of its size takes over. That handover happens in ports, in canals, in straits, at dry dock entrances, and wherever large ships and tight spaces exist in the same place at the same time. Ships are getting larger. The spaces they need to navigate are not getting wider. The tug is not a relic of an era before ships could steer themselves. It is a permanent solution to a problem that gets harder every time someone builds a bigger ship. And it will be doing this job long after everything else about shipping has changed.